Okay, so hold on a second. What's going on with that? Okay, that's good. Close that. Shut up. You guys can talk about these problems. It's not like I don't want you to talk. You can talk to each other. You just can't get a little close to each other. You're allowed to discuss the problems with each other. That is completely fine.
If you have any questions, you can come up and ask. You're allowed. If you want to check and answer, just finish the first two real fast.
you guys, hold on a second. Maybe,
And what can we do? I lost the I took the quiz out. I did it.
That's right, exactly. So you really,
Okay.
and you attached a picture, do you attach a picture?
I actually have the paper with
Oh,
my worksheet paper. Where I
okay,
did all the work on.
okay.
And I have the word problems too. I didn't know if you collected that or did that.
The ones that we went over that I gave on Friday?
Yeah.
We went ahead and they just kept working on those over the weekend.
Okay. Great.
Perfect, thank you.
Thank you. And did I miss anything on the first half?
All we did was go over some of the problems from that worksheet
Okay.
and just doing some extra practice problems.
All right.
It's okay. Did you find the time? How much did you find? Okay, that's fine. It's fine. Just It's stuff there. So then, just give me the clock with the numbers. Because I mean, if you said, oh, it's going to take this much longer, then look at you and go, what's wrong with you? Why are you talking so long? Logarithmic is riddles like that. You know, the propagate. What you have is that would be right, which is going to be kind of good, right? Okay, you're still okay. I can give her if you want that number. Huh? Yeah. That's good. You're still working on the work. That's all. Okay. How are you doing? Pretty good. Pretty good. A lot of stuff written down now. Okay. Got a lot of them. Looks like you started a lot of them. Yeah. Okay, that's fine. Okay, looks like you changed your mind on this one then. You know what you would have before in this? Oh no, I'm sorry. You're fine. Okay. What's that?
I have the original iPad.
I know. You have the hat, you have the picture. What was those? What did you? That's fine, that's fine. What is that? Lots of X order operations, you can't multiply these until you can 10,000. Okay, be careful on that. So did you go? So this is K. I like that. So now you have to go backwards, and now you have to be solving for K, you're going to be solving for t this time. So instead of being A3, you're gonna have something times t, and you're solving for t. So it's the same approach kind of. Okay? Yeah, what you did was great. Is that the final, like, which answer is that? Is that the final answer, or is that the, did you get an answer? Like, you have to work that out and give me a minute, so you're gonna have to do something like that. So you would give me an exact and an approximate after the half. I see what you get in there. That when you plug it in.
I'll take it later or not. I'm gonna scan this.
That way I can just put it up on the big board and check them later.
Which one makes the hardest in here? What do you think?
The last, like, 2 dashes.
So you think the very last problem is the hardest one, number 5, the hippie M56 problem?
Yeah.
Okay. What's the easiest one? I know which one I think is the easiest. You think the first one is? I think number 4 is the easiest. It's a straight out formula. Off your gold sheet, you're just solving for it. I think 4 is the easiest myself. And 2 is not real hard either. Just using the half-life model. I think I'm going to make this escape. Bring this over here. I'm going to set this up so each problem has its own page. Boop. Let's go ahead. Page. Escape. Okay, which one do you want to do? Let's not do number 1. Let's do one of the other ones. Yeah, what do you think?
5.
5. 5. So you guys need to have something to like do the calculations if we need to. Okay, so here we go. Hippium-56, a very unstable radioactive isotope, has a half-life of 55 years. Write an exponential function that will give the amount of a sample of 500 grams after 2 years. So that very first part, that should be straightforward.
using the function thing I've given you here. So I've given you that use for half-life models, y equals a times 1/2 raised to the t over HL is the idea, right? So for us on this problem, his initial amount 500 times 1/2 raised to the t, and for this particular thing, the half-life is going to be what? 55. So that part everyone should be able to write. Okay? That part everyone should be able to write using that gold sheet as, oh, okay, I'm just going to plug in what I know. So then it says, how long will it take the sample to decay to 5 grams? So I'm going to come down here a little bit lower. I'm going to do that in black right here. Okay, here we go. So that means I want this to be my new amount. 5 is going to go right here. So I'm solving this for t. I'm solving an exponent. If I'm solving exponentials, I'm going to use logarithms. Before I can go ahead and do anything, I have to get this all by itself. So I have to get rid of this 500. So I'm going to divide by 500 on both sides. Now you can leave it like this. You can even change it to a decimal because it's a nice decimal. Okay? This is 1 over 100, which is 0.01. So you can write it however you want. If it's a decimal that's a rational number, it can be written as a fraction, then you can write it as a decimal. I'm fine with that. Because you're not rounding. This is okay. So I'm just going to jump down to that bottom one now. 0.01 equals 1/2 raised to the t over 55. Let's just change it to logarithmic form. What would this be as a logarithm? Log base 1/2 of 0.01 equals the exponent, which is what? T over 55. How do I solve that for t? Multiply both sides by 55. So t is 55 times log base 1/2 of 0.01. That would be an exact answer for it. That would be an exact answer for it. Now let's go ahead for us, so we're going to write this, okay? We have to know what that is in years. I actually have to calculate that. So we do that, and we get that that is about how many years now? You tell me. I have an answer in front of me. Make sure you can enter that in.
365.4.
There we go. About 365.4 years. Now, at this point in time, what could I always do? Check it. I could always check. I could go back here and put 500. I could put 365.4 here, calculate this right-hand side, and see if I end up with about 5 here. I can check my answer to see if it works or not. So there we go. That's the first part of this, or that's the second part of the 4 parts of this. Any questions yet on this problem? Yes?
How would you type that into the calculator?
Are you using, so you're using that type, because there's all varying types here. All right. For you, I would type it in like this, 55 parentheses, and then I would do the next part. For you, you're going to have trouble with this, because you can't do log of any base. Let me just do change this one. You,
Okay, so this is what you mentioned.
yeah, because that would be the negation, and then I would type it in the log base 1/2 of 101, and it should be right. Yeah. All right. Got one of them. All right. So now let's go to the next one. Write a continuous exponential decay function for Hippium 56. A continuous. So now we're doing this. Okay. So let's think about this. Here's my original model. All right, there it is. Now I want to write it as a continuous model like this. That's a continuous model. Let's think about this now. Let's look back at this. Okay? What do I know? These have to be equal to each other. I know that. So E, I'm going to go back to red here. E to the RT is equal to 1/2 raised to the T over 55. Now this is where you need to understand that this E to the R, this and this are the same, and this is this. Power of a power property undone. So what do I know? That this is equal to that thing right there. I know E to the R now is equal to 1/2 raised to the 1 over 55 power. That's what I know. How do I solve that for R? Write it as a logarithm. R is going to be the natural log of this thing. There it is. Now that's an exact. Let's get an approximate for this because we're going to need that for the bottom one here anyways. So if I want now, I would take this and calculate it to get an approximate. An approximate for this one. Okay? And what do I get? See if you guys can get that on your calculator. What do you get for the continuous decay rate? We're actually finding this right now, and then we're going to write our function up here using it. Can somebody tell me what the continuous decay rate is? What'd you, Brady?
Negative 0.993.
I don't. Is that what you got? Anybody else get that? What'd you get? You get the same thing? You get the same thing? Maybe when my calculator was almost dead when I did it. Let me type it in here again.
Let me do this again one more time. I don't think you guys are putting it in there right. I'm not getting that. Did you get something different?
Yeah, I got to like the negative 0.01.
You know, what I'm getting, I'll just tell you what I'm getting. I'm getting negative 0.01260 if I go even further than that. Now here's what's going on. I want everyone to look at this because typing it into the calculator is the hard part, right? There's an easier way to think of this when you're putting it in your calculator. This right here is the same as R equals 1 over 55 times the natural log of 1/2. That is the same as the natural log of 1/2 divided by 55. That's the easiest way to do it on your calculator. Probably typing it in. There's no raising to a fraction then. So now, if you got that 90 something, do you get something different if you type it in like this?
When I typed it in,
Let me see.
I did that.
Aha.
Because
This is, okay, what it's doing is it's taking the natural log and then raising it. That's why it's not, yeah. If you want it that way, put that inside the parentheses and then it'll give you the right answer. Did you do it?
But I erased it too.
But you got the right answer now? Okay. Okay, so there it is. So now, this, okay, is what I get. Now what, and I told you this has got a 0 on it, okay? If you looked on your calculator. So it says, what is the continuous decay rate as a percent rounded to the nearest thousands? So if I move this over 2 to the right, it's negative what? Negative 1.260%. So the answer to this right here is negative 1.260%. And then if I want to write my continuous exponential decay function, let's go back to the red part of this. It would be y equals 500 times e to the negative 0.0126 t. There's the continuous one. Now we rounded it, but that's okay. All right. There's a lot going on in that problem. I understand that. Okay. So I think what I'm going to do is give you the answers to the other problems so you can check, okay? And then we'll go ahead and, if not today, if we need to tomorrow, that's fine. Tomorrow's, the last lesson we have left is a short one. There's no word problems involved with it per se. So that'll be a little easier probably for us to deal with. So let me give you the answers to the first problems. And then, now number one, there's a possibility of two things, okay? I read, when it says how much longer, that would be from the second reading, okay? So from the second reading, so from the 182, I think it was, is that what it was? Takes the thermometer, I know temperature, oh yeah, one here, boom. So from the 182, from that reading of after 3 minutes, it would be 7.69 minutes. If you had 10.69 minutes, you did it from the original reading. So I understand that, and a lot of you had 10.69. That wouldn't be how much longer, that would be how much total time. How much longer is from a period of time we've already gone past. So that's a little different. I'm okay with that though. If you had 10.69, I'd be happy. So from the 182, it's another 7.69 minutes. Okay. Number two, you get approximately 1,343 I put 486 years. Again, if you rounded that to 0.5, I'm completely fine with that. Okay? So 1343.486 is what I have for number two. Number three. Okay, I got to find my answer here. What is the half-life? Okay? So the first part, the half-life, HL, is equal to approximately 113.584. Okay? So that's the approximate. And then the half-life, the continuous half-life model would be, and I rounded this, so it's going to be y equals 84 times e to the negative 0.05, what's it out here? 03 t. Again, if you have negative 0.05 here, I'd be happy with that. Okay. So this would be the continuous model for Ms. Martin's isotope bondium. And then the very last one here, number 4, this one ends up being about 37.7 years. Okay. So those problems, you should be checking on those, seeing how you're getting those. Okay? And I will tell you, when we're doing the word problems in here, word problems, we're going to want an approximate answer always, because it's not going to make sense to give an exact answer. When we're solving equations that have no scenario, then I'm going to say, hey, make sure you give me the exact answer and the rounded one. Okay? Yeah. I sure can. And I actually tonight, after school, I will scan the answers with the work, and I'll put them online. You can check them tonight as well. That way when you come in tomorrow, you'll have a better idea of what you need to look at, but I'm not going to do it yet. But I'll put those on there, and I'll put them on tonight. So you can check them actually out there. Anybody here doing ACT stuff tomorrow? ACT prep? You are? You are? Okay. So the video, you'll want to, have you joined my YouTube channel?
Oh, yeah.
So you can go watch it because it'll just be up there later on today if you want to go see what happens in class. Okay? Have you done that too? Just join that and then you'll be able to go ahead and watch the recorded class.